running. The emerging space industrial complex, I think this involves the whole world, and I think it's going to be these integrated space ports and technology hubs. And this is where governments, I think, can help. I truly believe that space is a commercial operation, and it will be commercial. I think that where governments can help is to basically get their children to see the value of education and technology jobs, and that there is truly basically places for everybody. And, you know, we happen to farm in Australia, so therefore we bring in a lot of farming and agricultural technology. But I also think that it's an international sport. And this is another graphic, and I've again put the website up there because I don't think it's come out too clear on this. But this is actually quite good because I think it actually shows all the different parts of the economy. And there are things that we don't think of in space that are going to be important. For example, if we're on long-haul space flights, we're going to need entertainment. We're going to need variety in the menu. We're going to need how we get these people to cooperate. And this is my ideal picture when I eventually end up building our runway. We're waiting for space planes, but I quite like the design of this one. So this is, I think, where we have to actually really work together to ensure that we get the younger people in, we get the researchers, and there are places for technicians, and we need to stop what I consider scientific stagnation. As I said, there are, in 60 years of space sort of, you know, being up in Leo, we actually have not conquered a single medical encounter that we've had up there. But the engineers and the doctors need to come together. They need to actually come together, because there's no point in me saying, well, this needs working, but I need this device, without understanding how the device is going. In manufacturing, we have a lot of noise in Australia about manufacturing drugs up in space because we can purely bring it down. I don't actually see that as the manufacturing base. What I see as the manufacturing base in space is where we literally build spacecrafts in space, where we literally build what we need for space in space. And that's because mining off the asteroids are going to be closer to perhaps where we want to put a settlement. So I think it's a very exciting industry. It's one that seems to have wonderful international cooperations and lots of new friendships, and I think it's fabulous. And I think that it's an opportunity, though, that needs to be shepherded, managed, and perhaps directed just a little bit more, because it's not just about satellites. So there's my contact details down the bottom, fairly simple, Dr. Caswell at spaceportaustralia.com.au, and of course that's our website. Did I make the time?
Thank you. Thank you so much. This is really exciting information. You know, the suffered medical, so we have actually one of our students here is interested in human physiology. And for myself, I'm active in the space community. Very interested also in the whole, how can an analog astronaut community across Africa support some of this research, maybe in being a test bed for some of these new technologies that will be tested. Certainly, both in Australia has a lot of people who live in remote areas as well. So you have a lot of opportunity there as well to look at how do we actually test these technologies in real time. I will allow one question because it's a very technical question. And the technical question that somebody asked me is, how do you enhance oxygen? I'm not sure if it's a quick answer, but as quickly as possible, how do you intend to enhance oxygen?
Oh, well, we don't intend, we've done it. So that's the first part of the question, is it's actually already done. What we do is we upregulate the body to do the job itself. And I think there is a big difference between upregulating, or we're possessed worldwide with the genome, the genes, but we forget that we have the phenotype, and the phenotypic expression of those genes you can manipulate if you know how to do it properly. You need to also remember that humans are just a big sack of goo, and I like to say that quite literally, that humans are really the supporting act for the microbiome and for the mitochondria. And if we work with the microbiome and the mitochondria, we actually get the human to work better. And we just we fell into this sort of work mainly because my day work as a doctor, I work with skin. And one of the biggest problems on the ISS is skin. So the reason is that the environment actually changes the pH of the skin and it causes acne, rosacea, dry skin, and a whole lot of other things. So we wrote a little paper in 2022, which basically said, hey, this is how you fix it. It's very simple. And they all got very excited about it. But that was actually on the back of a lot of other work that we do for children with eczema and adults with, you know, as they age and the skin changes, how to actually make the skin better by getting the gut to work better. So with a bit of sort of esoteric research on the side, we realised that there are substances you can actually manipulate a little bit so that we can get the gut to work better. And the gut and the lung go together. And COVID taught this, I think, to a lot of people. But that if we upregulate a lot of the gut, we get the lungs to work better. Now, where we started with that particular project, because we always start with a problem and then work backwards, was basically, if you read a lot of papers on space medicine very closely, there's a huge cognitive decline. And it's because of the carbon dioxide toxicity. So that's going to be the longer you're stuck in a tin can and the further you go, so to speak, the worse I think the cognitive decline is going to actually be a problem. So if we are starting, you know, with the professional astronaut, they're probably all geniuses with 180 IQ. If you take 20 off them, you're probably not going to notice it too much. But the average person's IQ in Australia, 80 is what we considered disabled. So if we have an average of 100 as an IQ and we start to lose IQ points the longer we stay up in space, that can actually be quite disabling and then dangerous for the crew and dangerous for the mission. So that's sort of where we started. But obviously this technology that we've developed, it has earthside application for any what we call interstitial lung diseases or anybody who has problem with oxygen exchange. So really, I guess what we've done is provided the body with what it requires to work better, if that makes sense. That's the short answer. We can get into the long one later if anyone wants to be really bored with biochemistry.
All right, thank you so much. Thank you so much. Now we're going to move to Dr. Howard Chin. Dr. Chin, if you could please do something with your camera, if you could go into your video and remove the background because your face is going in and out. So look at your video on thing and just remove the background. Because we're seeing the organization background and your face is disappearing. Hopefully. And I'm going to go ahead and give you co-host so you can go ahead and share your screen. Are you ready? Your face is still being hidden. If you could, I can't read from here, so you need to do it from there. Go into the Zoom video and remove the background I've placed and just go no background, please. Is that possible? Oh, he's frozen. No, you see the dimming. Anyway, Dr. Chin? Dr. Chin? Okay, he's frozen. All right, so Dr. Mbenga, Dr. Mbenga, are you hearing me? Dr. Mbenga, are you hearing me?
Yes, yes.
Yeah.
Yes, I can hear you.
Please go ahead and present. We'll bring up Dr. Chin after you're done.
Okay, so
Yes.
I can't share a slide because of some technical difficulty here. But yes, thank you for having me. I will just you know, do a voiceover on what I intend to mention. So part of what I teach is space mission design, and the aspects that I thought I should cover, within these few minutes of speaking, is the project management, outlook of space mission. Want to design a space mission. What are the criteria? How should we be thinking? In the first instance, is what I think I will just talk about. So within the context of designing a space mission, a lot of time it looks cool and nice when we talk about a satellite mission, but the overarching objective is to think about what exactly is the mission about. Is it going to be an educational mission? Is it a mission to probably study disaster? Is it a communication mission? Is it a disaster monitoring mission? Is it for the military, or is it just an educational mission? That then helps us to understand what we should be doing within the context of the particular mission that we would love to design, and think about the different skills that will be required in terms of systems engineering. Most of the issues that we'll often find when it comes to thinking about or system thinking, or thinking about designing a mission, it's somewhat strongly related to skills, and then you start finding different skills, different gaps, within the within the skills peripheral of the. Sometimes you have people who understand the physics of what is to be designed. Sometimes you find people who have maybe companies who have commercial interest and are not thinking about the geopolitical context of it. And we just sort of now try to bring all of this together when we're envisioning our mission, or a mission design. So ideally, we look at what we call system context diagram, which I wanted to show, but I wouldn't be able to do that. So within your mission, we're looking at what is the architecture of the mission. So you have various people. Mostly what we do within when you are incubating a mission is to have all of the experts within that, people thinking through, oh, this is an agricultural mission. To have the agriculturist, you have the systems engineer, you have people who have different understanding of which orbit should this go to. You have the physicists who are there to do their calculations as to what should be the inclination of the satellite that you're trying to design, and you have everybody providing context, in order to just be able to have a successful design. So when you talk about the architecture of the architecture of the mission, is it's the fundamental and unifying system structure that you define in terms of what will be the elements of the mission that you're trying to design, the interfaces, the processes, and then you are thinking about the constraints, how will the behavior of all of these systems in the first instance. People are used to discussing satellites. We imagine that the mission defines what you will have as your payload. It also defines, you have the payload and then you have the bus. So the bus is the one that everybody sees. The payload is what tells you, defines the characteristics of that mission. What is it that you are able to, to bring on that mission. When so within the architecture of our system, it helps us to, you have a simplified top level, engagement, so to speak. It is going to be useful in terms of expanding on the system context. So you have a diagram that guides, all the procedure that will lead to being able to create that mission. And that helps us to create a top level architecture and that will capture the main elements of the system. So if we're designing, the other time I had experts or within the equatorial region as well as the high latitude sector together. I had applied to this funding, trying to design a mission that could help monitor space weather in the equatorial region as well as in the high latitude. And the science engagement alone, in terms of, I was the manager on the program, in terms of being able to manage the science of the equatorial region with the science of the high latitude, understanding what would then become the framework for our architecture, was, took us the longest because there were very many assumptions that we had made that we would just do this and do that. But when people who understand those science, I understand the science of the high latitude, when colleagues from the equatorial region provided their own input, we saw the complexity of being able to design such missions. We started seeing why we shouldn't do or implement some of the things that we thought we should do. And at the end of the day, we came to a robust conclusion wherein the systems engineers were then able to formalize the designs to be able to provide us an architecture. So within the architecture, sorry, I'm not able to show you my slide. I just have it here with me. You are looking at the mission or the purpose, the purpose of your mission. So you are trying to highlight that. You are trying to highlight the orbital trajectory. So which orbit is this going into? You are looking at the space segment. Where will this fit into, and all the other criteria that will guide in being able to come up with a robust outcomes. But basically, there are four major processes that one will also need to factor in. So you are defining the mission scope, and that would help to characterize your mission, or alternatives. You might say you want to do this. Maybe there are alternative ways that you could do the same thing. Probably you could cut down on cost. Probably it could be a less complex science and all of that. So, but we need to incubate that idea to be able to find such an alternative. The next thing will be that you are able to then select a baseline concept. So this is the concept. Now, so what is the baseline? What can we not do without? What must always be there? And the other things that could just be add-ons. And then that helps us to also be able to underpin the requirements for such missions. So basically, when you have those four project segments, you define your mission, you've been able to characterize your mission alternatives, their alternatives, you are able to select the baseline, your baseline concept, and then you are able to derive the requirements for, for such missions. And then that guides in being able to understand, you know, what you need to be doing. When designing the space, apparently, the thing you consider the space environment itself. You will need to consider the thermal, radiation, and the brain. And then you're considering the launch. You are looking at, you know, what's going to be the 5-ton launch vehicle. You're considering vibration and noise. Understanding that will you be able to access repair, redundancy, designing equipment to survive, then regulations, you know, cost, and the schedule. So these are some of the most important things that we will need to factor in when we then need to design, you know, a mission, either in any of our hospitals. I'll be able to take, you know, further questions because there seems to be a lot of, you know, in terms of the technical that I need to manage.
Okay. All right. Thank you so much. So a lot to unpack. There are a couple of people in the room may have additional questions. I certainly have some questions for Dr. Mbenga. It looks like we lost Dr. Howard, who actually wanted to talk about launch capabilities. I think he had some invention that he had. He actually had an invention there's a patent for. One of those conceptual inventions, which is a space elevator. A little bit ahead of our time here. But in the meantime, I wanted to ask about this issue of launch capabilities. Now, before that, the project management challenge, right? And I say it's a challenge because I'm not sure if the engineering, again, we're talking about developing an ecosystem, right? And I'm not sure that in the current engineering programming in African universities, there's sufficient opportunity for students to learn to manage simple projects, much less more complex ones. So what are some, because we want to really leave here with some action items, right? Now, we now have a whole bunch of space clubs that are being developed, not just in Nigeria, but I know in Kenya, I believe in Ghana. And also my latest thought experiment is to get legacy organizations like the Scouts involved in using their space badge model. So with these, because you know, university systems are hard to change and we don't have time. So as you think about this idea of working with the space clubs or legacy youth organizations, such as the Scouts, which have students in university in the senior, you know, the older groups of Scouts are in university doing rovers or whatever they call them. How do you see your project management concerns being addressed using those angles as opposed to waiting for the university system to change or even the organizations themselves to change? Okay. Dr. Beck, you heard the question?
So,
did you hear the question?
I think your question is how does the project management spectrum of
yes, I'm going to ask it again in a simpler way. How do you see Nigerian and other African countries using extracurricular spaces such as the space clubs and organizations like the Scouts and Girl Guides, where we can do space badges to begin to train the project management discipline?
Thank you. Thank you very much. I think that's a really brilliant and practical question that you have asked. So I think I can always point to what's been done in other places. Probably what I do in the institution where I work for, as an ideation for what's possible in Nigeria. So one is part of the things that we've done is, we've learned or we've taught students, on the ideation of or project management of space program from nothing. So when I mean from nothing, I mean, for example, I've been to primary schools in the UK to teach people on how to formalize rubbish rockets. And then I have school children with me. And then we design, so we need rubbish rockets. All we just need are, use bottles, something, a pump that we lift. And then we design that. We write things on paper. I, probably show puzzles to them. So tell me, what do you think is the most important thing? Is if you're designing this mission, is it thermal? Is it, heat that you will need most? Is it this? And then we fix those concepts. We sort out our puzzles. And then based on the puzzle, we transfer that to practical design. And these are things that will be done in 1 or 2 hours of just having, bright minds together. And within that, we've been able to, achieve the design of, say, a rubbish rocket, for example. We launch it with our foot, and then it goes up, and then we take all these pictures. So we use that as a first step, and then for students that are above that, whose reasoning is well above that, they come together as well. They start thinking about, okay, what if it's a CubeSat? What are we going to do? And then we have the students, working collaboratively, for example, from different universities. It might be a summer project. We have about, students from 4 or 5 universities working collaboratively, being supervised by some of us who know a little bit better than them, bringing out all of these concepts and asking them to ideate those concepts. And then we fix everything together. At the end of the day, maybe at the end of 3 weeks, we are able to come up with with a concept that is physics based, but practically practical inclined, that we've been able to design. And that way, those students, you find them asking the right questions. How can we do this? We understand the gaps that might be missing. And at the end of the day, right now, it's the same student. We're designing a mission, a CubeSat that will cost about £1.3 million. But this was how we started with these students. We did the rubbish work, first of all, look for things that are not, we did it on in an open class. Then we took it to the next level. We thought about the things that are necessary. We invited companies and people who already, who are already in the satellite design industry. The student will ask us the right questions, and then we incubate the idea, we turn it to something really good, and then we have our 3 universities, bringing the money together with the help of the companies, and then we've now designed a CubeSat that is ready to be launched January 2026. So these are practical ways that we can implement these projects, and then augment them to becoming something really useful that will actually get to the point of being launched.
Thank you so much. I think we're out of time. But Dr. Caswell, I have one action item because I like to leave it with an action. So as you know, this October, our theme for World Space Week is living in space. So we would like you to suggest a low ball, not highly technological simulation that we might do as analog astronauts. We hope to have a physical location in Kenya where we will have 30 people simulating a lunar habitat. Beautiful. So if you can come up with a suggestion of some off-the-shelf sensors that we might be able to use that might provide a quick experiment, or simple, I shouldn't say quick, simple experiment that can be done over the course of, let's say, it's a 10-day, well, no, it's a 7-day stay. So let's say of the 7 days, we have 5 days of experiment, because the first day is, load in, last days move out. So 5 days of some kind of experiment that might offer an opportunity for young people who are just starting out to begin to think like how people at your level are thinking. Give them some beginning skills that might be relevant for learners, early learners in the ecosystem of space physiology.
Well, right off the top of my head, the first thing you can do is you could, if you really wanted to, a split face experiment. So what you do is you just swab left and right of everybody's face, and on the right side, we might put a solution, just white vinegar, nice and easy, twice a day, but the left side not. And at the end of that, you swab them again and you compare what the microbiome is. That's nice and easy. You just need some lab to be able to grow the microbiome. The second thing you can do, and this one is a little bit more interesting, before we have everybody load in, you swab the main communal surfaces. So tables, chairs, benches in the communal areas. You grow those swabs, you wait the 5 days, and then you re-swab all of them. Because one of the things that I think that shows to a lot of people is just how much we spread and how much cross-fertilization happens. So for the audience that might not know, when we put people in an enclosed environment, we all have what we call a microbiome, or the bugs that live in our gut, unique to our genetics. Okay, so it's familial, but it's also tuned to your genetics. So mine will be different from yours, madam, and that actually will be dictated a lot by our diet, our environment, and where we live. Now, what happens when we put people in these enclosed environments becomes generic. So we don't know how it happens. Even with the best aseptic technique, it becomes generic. But I think in this environment, a simple technique is that if we have a sterile environment, but it's not always sterile, that's why we do the pre-swabs and do the end of the week swabs, just to actually see maybe what species of bacteria actually are robust and technically hang around. I think that's always important information, and it doesn't seem like much until you start understanding that all these creatures in your gut, some 2,000 of them, just to give everybody the heebie-jeebies, they control your hormones, they control your growth, they control your mood, they control your nutrition, they control everything. So if you are genetically tuned and it changes on you, now the more extensive one, you do have to deal with the poop. So probably not this group, but that's maybe something to plan for in the future when you have a longer analog, is we analyse beforehand and we analyse at the end. And I think these are the types of things, it's really interesting. We just gave a big panel at asthma in America, and our panel was actually about what we call biological life support systems. So at the moment, we have what we call physical chemical life support systems. So these are all your engineers and everything, but that's not going to sustain in space because we can't send the supplies up to run the chemicals. So we have to swap to what we call a biological life support system. So we modeled it for everyone, given the information, but one of the pharmacists I worked with gave the first talk. And as he actually said, if you all remember War of the Worlds, at the end of the day, it wasn't our ingenuity and our weapons that saved humans. It was actually the bugs. The bugs killed the aliens. And I think this is important. We carry them with us. They are part of us, and they will change in space because they actually replicate 5 to 10 times faster in microgravity. So we'll leave that for another discussion. But it's important that we start wiring how people learn to manage what we would term the macro environment. So
Yes.
their spaceship, because it's going to be very important for people in space. And if we have an understanding of how things spread, how they get around the room, and remember that's very different to how it spreads in a hospital, because this is a normal social. So there are two things I can think of straight up. That'll keep them busy.
Thank you so much. Thank you so much. We have come to the end of a very interesting session. Unfortunately, Dr. Chin, who's going to talk about rocket launching from Nigeria, he has internet capability issues. He's calling in from Jamaica, so he has internet capability issues. But we're joined now by our next